Good day, guys. Let's start with Unit 2 topic basic structure of a computer. Okay, so what are the types of computer that is available? So there are 6 to 7 types of computers: microcomputers, laptop computers, workstation, mainframes, supercomputers, handhelds, and multi-core computers. You know what is a workstation, what is a laptop, and what is a desktop. We'll see what is supercomputer. The supercomputer is a computer that is considered to be fastest computer in the world, used to execute tasks that will take a lot of time for other computers. So these type of computers are basically used to model weathering, weather systems, genome sequence, etc. Okay, so refer HTTP mm, uh, colon double slash slash www top500.org. See the some of the fastest computers. Next is mainframe computers, large expensive computer capable of simultaneously processing data of hundreds of thousands of used to store, maintain, and manage large amount of data that is needed to be reliable. Next is handle. It is nothing but a PDA, personal digital assistant, a computer that fits in a pocket, runs on battery, and used while holding the unit in the device. So basically, we use it for purpose like appointment book, address book, calculator, and notepad. And multi-core computers are computers that have multi-cores, parallel computing platform. Many cores are computing elements in a single chip. So examples are Core 2 Duo, i3, i7, and so on. So we'll get into the functional units of computer. Basically, the functional units of computer are input unit, output unit, central processing unit, which consists of ALU and control unit, memory unit, and the bus structure. So this is the basic diagram of a functional unit. If you see inside the central processing unit, you have cache memory, operational register, program counter, arithmetic and logic unit, and the control unit, which is worked on by instruction sets and given from outside. So all computer functions are mainly four things: data processing, data storage, data movement, and control. So data is nothing but information. Okay. So the operational concepts, basic function of a computer to execute a given task as per the appropriate program. So program consists of list of instruction that is stored in the memory. So let's see a typical instruction. So a typical instruction will be something like this: add or not comma LOCA. So in according to the instruction, the operand at the memory location LOCA is added to the operand in the register or not. So then once the addition takes place, what happens? The addition sum is placed in the register or not. The original contents of LOCA are preserved, whereas the contents of our register or not is overwritten. So load R2, LOC. In this case, what happens? The contents of the location, memory location LOC is moved into the R2 register. So the LOC contents are preserved here, whereas the contents of R2 register are overwritten. The first, the instruction is fetched from the memory into the processor, then the operation to be performed is determined by the control unit. The operand of the LOC is fetched then from the memory into the processor. Finally, the operand is stored in R2 register. Next is add R4, R2, R3. So they add the contents of R2 and R3 and store it in R4 register. The operand in R2 and R3 are not altered, but the previous value in R4 is overwritten. So next is store R4, LOC. The instruction copies the operand in register R4 to memory location LOC. The original contents of LOC are overwritten, but those of R4 is preserved. So this is a simple diagram which shows the connection between a processor. So in this, according to this diagram, if you see, the processor has these things: MAR, MDR, program counter PC in instruction register IR, R0 to Rn-1, general purpose register, control unit, and the ALU. And you have memory unit and input unit on the other side. The system bus connects these two units to the processor. So if you look at it, there is a single way connection between MAR to the system bus and dual way connection between MDR and control unit to the system bus. Likewise, memory and input and output unit has a dual way connection. So this is what it is, which I told you just now. So let's see how data transfer takes place. So program gets into the memory through an input device. So basically, for the program to get operated, first the starting address of the instruction has to be told. This is told by the processor. So the what processor does is it places the starting address in the program counter. So once the starting address is in the program counter sends this address to the MAR. MAR is our memory address register. So you using this, the memory address register initiates a read control signal. So once the read control signal is initial, the addressed word is read out from the memory and loaded into the MDR. The contents of the MDR is then transferred to the instruction register for instruction decoding. So the operation field of the IR is examined to determine the type of operation. The fetching the operands from the memory requires sending the memory location address to MAR and initiating a read cycle. The operand is read from the memory into MDR and then from MDR to the ALU. So then to fetch the data again, the program counter uh, what happens in the program counter basically is once the first instruction is fetched or once the first instruction is pushed into the MAR, the next instruction is loaded into the program counter. Usually the instructions will be loaded in consecutive memory location. So PC will be PC plus 4. So next is interrupt. An interrupt is a request for IO device for service by processor. Processor provides requested service by executing interrupt service routine, that is ISR. Contents of PC, general register, and some control informations are stored in the memory. When ISR is completed, processor restores them from the memory. Next, we'll see about the bus structure. So connecting CPU and memory. What a bus structure does is it connects CPU and the memory. So the CPU and memory are normally connected by three buses: data bus, address bus, and control bus. So as shown in this diagram. So a group of bus is nothing but a group of wire which carries information from CPU to peripheral I vice versa. So single bus structure, common bus used to communicate between the peripherals and the microprocessor. So the drawbacks is it's relatively slow. See, buses vary widely in their speed of operation. Some devices are relatively slow, like printer or keyboard. Some devices are considerably fast, such as optical disc. So memory and processor units operate as the fastest part of the computer. So when you use a single bus algorithm, the data transmission due to slow speed devices pull down the overall speed of the system. So to overcome this, what happens is they include buffers, and before the data is put into the bus, the data is buffered into these registers, and then when full data is come, they are moved to the bus. Another way of doing it is two bus structure. One bus can fetch instruction, and other bus fetch can be used to fetch data required for execution. The bus is said to be performing two distinct functions. The main advantage of the structure is good operating speed, but on account of more cost. So this is a diagram of two bus structure. So this is where we have multi-bus structure. So in this case, there is different bus for address, different bus for data, and different bus for control signals. So by using 2 to the power 3, that is 3 address lines is used to select 8 locations. In general, 2 to the power is equal to n, where x is the number of address lines and n is the number of locations that can be addressed. So address bus is unidirectional. That is only group of wires which can address information to the form from processor to the peripherals. Next is data bus, bidirectional group of wires which carry data information processor to the peripherals and from peripherals to the processor, and control bus is bidirectional again from processor to the peripherals and vice versa. So figure 2 shows address, data and control bus and their connection with the peripherals. The next important topic is memory locations and address. So memory consists of millions of storage cells, each of which can store 1 bit. Data is usually n bit. So n bit is called word length. The memory of a computer can be schematically represented as shown in the diagram here. So first word, second word, and eighth word and last word. So the memory of the computer can be schematically represented here. So the memory is the second major subsystem in the computer. It consists of locations, uh, storage location, each with unique identifier called the address. So data is transferred from memory in group of bits called words. A word can be 8-bit or 16-bit or 32-bit or 64-bit. If it is 8 bits, it's called a byte. If it is 16-bit, it is called 2-bit wide. If it is 32-bit, it is called 4-byte word. So address space to access a word in the memory requires an identifier. Although programmers use a name to identify a word at hardware level, each word is identified by an address. The total number of uniquely identifiable location in memory is called the address space. For example, a memory of 64 kbps and a word size of 1 has address space that range from 0 to 65,535. So memory addresses are defined using unsigned binary integers. So kilobyte is 2 to the power 10, megabyte is 2 to the power 20, gigabyte is 2 to the power 30, and terabyte is 2 to the power 40. So let's see an example. A computer has 32 MB of memory. How many bits are needed to address any single byte in the memory? So the memory address space is 32 bytes, uh, 32 MB. So which is, I can write it as 2 to the power 5 into 2 to the power 20. So this means we need 25 bits to address each bytes. Next is a computer has 128 MB of memory. Each word in the computer is 8 bits. How many bits are needed to address any single word in the memory? So the memory address space is 128 MB, which means 2 to the power 27. So for each mm, word, I need 8 bytes, which is 2 to the power 3. So from 2 to the power 27, I have to remove my 2 to the power 3, which makes it 2 to the power 24. That is 24 bits are needed to address each word. So memory operations. So there are basically two types of memory operations. First is a load operation and second one is store operation. Load operation is also called read or fetch. Contents of the memory are loaded into the processor, and store operation is called write operation. So data from the processor is processed and stored in the memory location. So assignment of byte address, we have two terms to describe the order in which sequence of bits are stored in the computer. One is big endian and next is little endian. So big endian is an order in which big end is stored first. So most significant value in the sequence is stored at the lowest storage address. And little Indian is in which little, that is least significant value, is stored in the first location. So in this case, um, first example is big Indian. So in the big Indian, what happens? The the most biggest value is stored in the little address. So zero x 100 is the biggest value. That is starting value. So 0, 1, 23, 45, 67 is the number. And in case of Little Indian, the least value is stored in the um, smallest address. So in this case, 67, 45, 33. So the number is actually 0, 1, 23, 45, and 67. So Little Indian, lower order byte stored at lower address, byte 0, byte 1, byte 2, byte 3, and in example 46, 78, 96, 54 are the bits. So in this case, 54 is the lower byte. So in Big Indian, higher order byte stored at lower address. So this is how it is. So this is Big Indian and Little India. So next is instruction and instruction sequencing. So instruction is a command given to the processor to perform a given task. Instruction set is an entire group of instructions, and instruction sequence is order in which these instructions are executed. So there are four types of operations in a computer using instruction: data transfer between processor, memory and processor, arithmetic logic operation, program sequencing and control, and IO transfer. So data transfer instructions are, they are also copy instructions where data is moved from one location to another. So some of the instructions are MOV, LDA, STA, push and pop. So MOE is copy this from the source to destination. LDA is load the accumulator. Accumulator is a special purpose register. And STA is store the accumulator. Push is push the register pair onto stack, and pop is pop out from the stack to the register pair. Next is data manipulation instructions. There are three categories: arithmetic instruction, logical and byte manipulation instruction, and shift instructions. So arithmetic instructions are INC, DEC, add C, and mul. So INC is nothing but increment the data by one. This DEC is decrement the data by one. Add is add perform sum of data. Add C is add with carry bit, and mul is perform multiplication. Then logical and bit manipulation instruction, and or not or exclusive or. So bitwise AND operation, bitwise OR operation, invert each bit of a byte or word, and exclusive OR operation over each byte. So instruction format, an instruction in computer comprise of groups called fields. These fields contain different information. The most common fields are operation field, address field, and mode field. Operation field specifies the operation to be performed like addition, subtraction. Address field concerns the location of the operand. Mode field specify how to find the operand. So instruction is of various lengths depending on the number of instruction. So basically there are four: zero address instruction, one address instruction, two address instruction, and three address instruction. So let's see about these three instructions. So if a process, we'll see starting with one address instruction. So in one address instruction, sorry, zero address instruction. In zero address instruction, we use stack to manipulate it. For example, I want to evaluate the expression a plus b into c plus d. Then what I'll do, I'll push a, push b, add, push c, push d, and add mul and pop x. So in first step, push A takes place, push B takes place, and both A and B are added together. Then pushing C and D, then addition takes place between C and D. Then you are multiplying the addition value of A and B with the addition value of C and D, and then you're copying the result to X register. So in this, there is no memory location that is specified in this zero address instructions. So in one address instruction, operation and source or destination is given. So it will be something like add B, load D, add E, and something like this. The other location will be, see, in add D, where what will be D added to? That is the contents of the accumulator. Likewise, when I say add E, E is added to the content of the accumulator. So in one address instruction, always one location will be the accumulator. Okay. So the same exception in case of one address instruction, it will be load A, add B. So when I say load A is loaded into the accumulator. When I say add B, B is added with accumulator content, which is A. Then I'm moving store T. The accumulator content is stored in T register. Then I see load C and add D. C and D are added. Then I say mul T. So the contents of accumulator are multiplied with T content. That is, content of accumulator is C plus D. And when I say multiply, it is multiplied with A plus B, and store X content is moved to the storage. Two address instruction, syntax is operation, source and destination. So there will be one source and one destination. Move of E comma F, add of D comma F. These are some of the examples. So we'll see the same example. So move R1 comma A, add R1 comma B. So first A is moved to R1, then you add A with B using R1 comma B. Then move R2 comma C and add R2 comma D, and then I say mul R1 comma R2 and move X to R1 register. So this is two address instruction. In three address instruction, you will have source 1, source 2 and destination. So add of D, E, F. So the contents of D and E are added with, it's added and stored in F. So if you look at in the same example in three address instruction, add of R1 comma A comma B. So one step I have added A comma B, and in second step I am adding C comma D, and third step I am doing the multiplication. Okay, guys, this is a very important 10 marker when it comes to exams. So next is instruction cycle, the basic operational process of a computer, also known as fetch decode cycle. So what happens in fetch decode cycle? First step, fetch the instruction. Next is decode the instruction, read the effective address and execute the instruction. These are the steps that occur during a instruction cycle. So next is conditional codes. The conditional codes are negative, zero, overflow, and carry. Negative is one if the results are negative, zero if it is positive. Likewise for everything. Next, we'll get into the addressing modes. So basically, there are n 1, 2, 3, 4, 5, 6, 7, 8, 9 addressing modes: immediate addressing, direct addressing, indirect addressing, register addressing, register indirect addressing, relative addressing, index addressing, auto increment, and auto decrement. So different ways in which the location on operator can be addressed or specified in the instruction is called addressing modes. So we'll see about all these address mode in detail. So the first is immediate address mode. In immediate address mode, we don't have any memory location. The operand, the content of the data is directly given in the instruction itself. So when I say add 5, 5 is added with the contents of the accumulator. So what is the problem? No memory reference to fetch data, so it is fast. But the disadvantage is it has a limited range. So next is direct addressing. So the address field contains the operand of the data. So when I say add A is the address where you have to fetch the data. So the effective address is the address field A. So the advantage is single memory reference to access data, no additional calculation to work effective address. Again, limited address space is the disabled. So it is something like this. The address A will be given with the pointer to the data in the memory. So in indirect addressing, memory points to an address field containing the address of the operand. So effective address is look in A, find the address of A and look there for the operand. Add of A will be an address, go to the address and that address will point to the memory location. So it is something like this. Okay. So that is indirect addressing. So next is register addressing mode. In this, the operand is contained in a register set. So no memory access is needed, very fast execution, but very limited address space and very limited number of registers. So add R, so the contents of register add are added to the accumulator content. This is similar to direct addressing mode. Only thing in instead of a memory location, we use a register here. Okay. Next is register indirect addressing mode. It is pretty much like indirect addressing mode. You find an address in the register and you go to that address, you will find another address where the data is stored. So that is register indirect addressing. Next is index addressing. So in case of index addressing, the content of the index register plus the address part of the instruction is the effective address. So you will be given an address and also you will be given the index register. One address will be there. So you have to add both this, you will get the effective address. So you here you have your address. So, and the relative address and contents of the program counter plus the address part of the instruction. So, in index addressing, the address of the contents of index register, but in case of relative addressing, it is content of the program counter. Next is auto increment mode, a special case of register indirect addressing mode where effective address is the content of the register. Okay, so after the contents of the register is added, the address is automatically incremented. Okay, so first it is showing 3300. Once you take the data 6B, the content, the address will be automatically incremented to point to 3302. So in case of auto decrement, the content of the register minus step size. First, the content of the register is decremented, then the data is accessed. So first itself you decrement the day value and they access the data. That is auto decrement mode. So let's see a case study of 8086, which is one of the most initial process. So what is microprocessor? Is a CPU on single chip. And then what is microcontroller? If microprocessor is its associates support circuitry and memory and peripheral I/O components are implemented on a single chip, it is a microcontroller. We use AVR microcontroller as an example in this study. So if you look at this diagram itself, you will know what is the difference between a microprocessor and microcontroller. So if you look here, this whole thing is a microcontroller. So it has processor, it has memory and I/O ports. Whereas in a microprocessor, I have only the CPU, memory and I/O ports are added to it. So what is the difference between these two? CPU standalone, CPU, RAM and timer are single chip. Designer can design an amount of ROM, but here it is fixed. It is expansive, not expansive. General purpose, single purpose. Microprocessor based system is complex and expensive. Microcontroller is rather simple and cost effective. The instruction set is complex with large number of instructions, whereas it is very simple with less number of instructions. So this is the internal structure and basic operations of a microprocessor. So actually it has ALU, register section and control and timing section. So microprocessor performs three main tasks: data transfer between itself and memory or I/O systems, simple arithmetic and logical operation, program flow via simple decision. So there are n number of microprocessor types. They are characterized by the word size. You call them as 8-bit microprocessor, 16-bit microprocessor, or 32-bit microprocessor. And second thing is they are also characterized by their instruction set structure. You have two types, RISC and CISC. That is reduced instruction set computer and complex instruction set computer. And by functions, general purpose, special purpose, such as processing, image processing, floating point calculations. So 8086 is one of the initial microprocessors designed by Intel in 1976. It is a 16-bit microprocessor having 20 address lines and 16 data lines. Provides up to 1 MB of storage. Maximum mode suitable for having multiple processor. Minimum mode is suitable for single processor. Features is first 16-bit processing having 16-bit ALU, 16-bit register, internal data bus, and 16-bit external data bus. Uses two-stage pipelining, fetch and execute stage. Can prefetch up to 6 bytes of instruction and store them in a group. So the general purpose registers are accumulator, which is a 16-bit register divided into 8-bit AH and AL. AH is 8-bit higher order bit and AH bit lower order bit. Next is base register, 16 bits divided into 8-bit registers BH and BL, used to store value of the offset. Then CS register, it a counter register. You use this for looping and rotation. Again, it is a 16-bit register. DX is data register. This is where you store your data when you do addition, multiplication, and such type of operations. Next is stack pointer. It is 16-bit address. Again, it is used for stack operations. And BP is base pointer, 16-bit register used in accessing parameters passed by stack. Next is SI, source index register, a 16-bit. Again, its offset is relative to data segment. Next is DI, destination index register, 16-bit, again used in pointer addressing of data and as a destination in string fields. IP is instruction pointer, 16-bit, stores the address of the next instruction to be executed. Then there are 4 segment register: code segment, data segment, stack segment, and extra segment. Code segment, the users cannot modify the content of this register. Only the microprocessor compiler can do it. In data segment, the user can modify the contents of the data segment. Stack segment is used for stack operations, mainly push and pop. Extra segment is used for the control of the compiler in DS, where we can add and modify the instruction. So flag or status register, 16-bit register contains 9 flags. Remaining 7 bits are idle. These flags tells the status about arithmetic and logical operations. If the flag value is 1, the flag is set, and 0 if it is reset. So a digital microcomputer block diagram. So this is also called as a personal computer, which consists of microprocessor with ALU, control unit, and register array, and input and output unit work on it with in conjunction with micro memory unit. So with this, second unit is done. Thank you.